Yeah, welcome to Easy Mathematics and a new video. Today's topic is a funny ratio of binomial coefficients. I spot a couple of days ago and I thought about a challenge for this. I have no idea. I'm pretty sure that this funny result is not new. I'm pretty sure I'm not the first who thought about this, but I had no source who in the past time was involved for this funny statement. Yeah. So let's see what we want to do. So first I talk about some requirements, then I make some recalls, then we take a look at the curious property, and then I show the challenge. Alright, so let's go. So in this video I assume that you've heard about the binomial coefficients. I will not talk so much about them. I just want to recall a couple of important properties we will use here, okay? So the binomial coefficient is defined for natural k and n, if k is in between 0 and n inclusive. And how we can define it: n choose k is n factorial over k factorial times n minus k factorial, where n factorial is the product of the first consecutive natural numbers, and we define 0 factorial equals 1. Okay. Then there is also a nice recurrence relation. Yeah, you know, n choose k is n minus 1 choose k minus 1 plus n minus 1 choose k for n greater 0 with initial values n choose 0 and n choose n is 1 for all n. And I just want to show, if you haven't seen that, you can order the binomial coefficients in a triangle called the Pascal triangle. The left and the right side of the triangle is all ones, and all missing coefficients greater 1 you get by this relation. And for the triangle, this means you add the two numbers above left and right diagonal. Okay, so here 6 and 4 is 10. Okay, all right. So what is the curious property? It looks not so curious in the first moment. This is the ratio of two consecutive binomial coefficients is k plus 1 over n minus k. And of course you can prove this. You write both binomial coefficients and then you cancel out the common factors. Okay, this is very easy to get. But what is funny in this property? I showed this in the Pascal triangle. Let's see. Okay. So here down I've written the relation again, and what is funny here, and if we take a row in the Pascalian triangle, then we know there are n plus 1 binomial coefficients in a row. Okay, and if we take two consecutive binomial coefficients, then here on the left side we have k plus 1 binomial coefficients, and on the right side they are n plus 1 minus k plus 1, so n minus k binomial coefficients. And if you take a look at the statement, these two numbers are exactly in the ratio. And this is my funny property. Yeah, so the ratio of two consecutive binomial coefficients is the same ratio of the length of these two segments, I say. Okay, this is quite interesting. And yeah, I thought about a challenge, like I said. And what is this challenge? Let n greater be 0 be natural, and consider the family of fractions capital F of n is the set of the ratios of the form k plus 1 over n minus k. So these are exactly these ratios, where k is 0 included but n excluded. Okay. Define capital R of n is the set of all elements of capital F of n with the property that the fraction is reducible. Alright? Show that the number of elements in the set capital R of n is n minus phi of n plus 2, where phi of n is the Euler's quotient function. Yeah, thanks for watching. See you next time. Bye bye.